The reawakening of Magnetar, a city-sized star named XTE J 1810197 born from a supernova explosion, was an incredibly violent affair. After a decade of silence, one of the most powerful magnets in the universe suddenly burst back to life in late 2018. The snapping and untwisting of the tangled magnetic field released enormous amounts of energy as gamma rays, X-rays, and radio waves. By catching magnetar outbursts like this in action, astronomers are beginning to understand what drives their erratic behavior. Scientists are also finding potential links to enigmatic flashes of radio light seen from distant galaxies, known as fast radio bursts. Magnetars are young neutron stars with magnetic fields billions of times stronger than our most powerful Earth-based magnets. The slow decay of their magnetic fields creates an enormous amount of stress in their hard outer crust until it eventually fractures. This twists the magnetic field and releases large amounts of energetic X-rays and gamma rays as it unwinds. These exotic stars were initially detected back in 1979 when an intense gamma ray burst emitted by one was picked up by spacecraft across the solar system. Since then, we found another 30 Magnetas, the vast majority of which have only been detected as sources of X-rays and gamma rays. However, a rare few have since been found to also emit flashes of radio waves. The first of these radio-loud magnetars goes by the name XTE J 1810197. Astronomers initially discovered it as a bright source of X-rays after an outburst in 2003, then found it emitted bright pulses of radio waves as it rotated every 5.54 seconds. Unfortunately, the intensity of the radio pulses dropped rapidly, and within 2 years, it had completely faded from view. XTE J 1810197 remained in this radio silent state for over a decade. On December 11, 2018, astronomers using the University of Manchester's 76-meter Lovell telescope at the Jodrell Bank Observatory noticed that XTE J 1810197 was once again emitting bright radio pulses. This was quickly confirmed by both the Max Planck Institute's 100-meter Effelsberg radio telescope in Germany and Mariam Cicero's 64-meter Parkes radio telescope in Australia. Following confirmation, all three telescopes began an intense campaign to track how the magnetar's radio emission then evolved over time. The reactivated radio pulses from XTE J 1810197 were found to be highly linearly polarized, appearing to wiggle either up and down, left to right, or some combination of the two. Careful measurements of the polarization direction allowed us to determine how the magnetar's magnetic field and spin direction are oriented with respect to the Earth. Diligent tracking of the polarization direction revealed something remarkable. The direction of the star's spin was slowly wobbling. By comparing the measured wobble against simulations, scientists were able to determine the magnetar's surface had become slightly lumpy due to the outburst. The amount of lumpiness was tiny, only about a millimeter off from being a perfect sphere, and gradually disappeared within 3 months of XTE J 1810917 waking up. Normally, magnetars only emit very small amounts of circularly polarized radio waves, which travel in a spiral pattern. Unusually, we detected an enormous amount of circular polarization in XTE J 1810197 during the 2018 outburst. Observations with Moriam revealed the normally linearly polarized radio waves were being converted into circularly polarized waves. This linear to circular conversion had long been predicted to occur when radio waves travel through the superheated soup of particles that resides in neutron star magnetic fields. However, the theoretical predictions for how the effect should change with observing frequency did not match observations, though weren't too surprising. The environment around a magnetar in outburst is a complicated place, and there are many effects that can be at play that relatively simple theories aren't designed to account for. The discovery of the slight wobble and the circular polarization in the radio emission of XTE J 1810197 represents an exciting leap forwards in how we can study the outbursts of radio loud magnetars. It also paints a more complete picture of the 2018 outburst. We now know that cracking of the magnetar surface causes it to become distorted and wobble for a brief period of time, while the magnetic field becomes filled with super hot particles whizzing about at almost light speed. Combined with other observations, the amount of wobble could be used to test our theories of how matter should behave at densities much higher than could ever hope to replicate in labs on Earth. The inconsistency of the linear to circular conversion with theory, on the other hand, motivates us to devise more complex ideas of how radio waves escape from their magnetic field. While XTE J 1810197 remains active to this day, it has since settled into a more relaxed state with no further signs of wobbling or linear to circular conversion. There are, however, hints that both phenomena may have been seen in past observations of other radio loud magnetars and might be a common feature of their outbursts. Like cats, it's impossible to predict what a magnetar will do next. But with current and future upgrades to telescopes in Australia, Germany, and North America, we are now more ready than ever to pounce the next time one decides to awaken. Thank you for watching. If you've enjoyed our videos, subscribe to our channel for there's more to come.